Okay folks, we're going to start looking at optimization problems. Optimization problems are a type of calculus word problems that are applications of our first derivative test. And so we're going to be looking at how do we analyze the word problems, and then we're going to be using our skills that we've developed with first derivative test. The first thing that we should talk about are some strategies to get us started. So we'll make a list of things that we're typically going to do to solve an optimization problem. The first thing that we're always going to want to do is make sure we have a picture. So we need to sketch a picture if necessary. After we sketch a picture, we're certainly going to read the problem and identify any interesting and particularly useful information. But our goal is to figure out what quantity is being optimized. And what we mean by optimized is we're trying to find the max or the min of something. And that's why it's an extension of the first derivative test. Once we've figured out what quantity is optimized, then we're actually going to write an equation about that quantity. Now, after we've written an equation about that quantity, we need to make sure that that equation is in terms of only one variables. And then last but not least, we get to do the first derivative test. These 4 steps are probably worth putting in your notes in sort of a box of knowledge, something that you can find and refer back to whenever you get stuck on an optimization problem. It'll give you a place to start. Now, our plan for today is to look at some classic optimization problems. And frequently, optimization problems are going to fall into categories. At first, they're going to feel super icky, and then after we try several of them, you'll kind of get a sense of, okay, I've maybe seen one of these before. The first of our classic optimization problems is called a fence problem. So let's get started with the fence problem. Let's take a look. This fence problem tells us that we have 80 feet of fencing, right there, and we're going to build an enclosed garden. And we're pretty savvy folks. We've decided that we're going to save money by using one side of our house as a side of the garden. And then in the end, we're trying to figure out what should be the dimensions of the fence when we want to maximize the associated area. So we're looking for dimensions. We're trying to maximize area. Well, let's get started with our first step. Our first step says to draw a picture. So over here on the side, I'm going to draw the edge of my house. And then we're going to imagine drawing a rectangular fence in garden area. So we have our plants and our flowers in here. Now we have no idea what the length right here and the width of our garden is. So let's just label those with variable names for the time being. So I'm going to call this side X. I'm going to call this side Y. This side, since it's a rectangle, is also going to be X. Now using this information, we're going to be able to write some equations to help us out. Now next on the list, it asks us to figure out what we're optimizing, what we're maximizing or minimizing. And I noticed that we're maximizing the area. So that means over here to the side, I had better write an area equation. Okay. Now, we're pretty smart cookies. We know that to find the area of a rectangle, you just take the length times the width. So my area formula is X times Y, which is great. Now we have a slight problem in that area formula is in terms of 2 variables, X and Y. That's a problem. So what we're going to be using is some other information to help us get rid of or substitute out one of those variables. In particular, I'm going to go to the side. I know based on the problem that we have 80 feet of fencing. So that has to mean that the sum of these blue pieces, that's my fencing, has to be 80. So let's write an equation that says that X plus Y plus X equals 80. Or we could say 2X's plus Y equals 80. Now what we can do is we can solve this black equation for one of my variables, and then we can substitute that in over here. Now it looks to me like solving for y would be the easiest, so let's subtract 2x's from both sides. And now we're going to take that and substitute it in for y for our area formula. Here we go. So we end up with a equals x times 80 minus 2x's. We are much happier now because we only have one variable right there. Now the next thing that we're ready to do is optimize. So we're going to do the first derivative test to help us find the max and the min. Now we know that first derivative test forces us to find the derivative of this guy. Now I'm looking at this pink thing. I think it would be a little easier if I distributed this x in before I took the derivative. So let's do that. I got 80x's minus 2x squareds. And now finding my derivative is really easy. No need for a product rule. Here we go. A prime equals 80 minus 4x's. Now we know that the first derivative test tells us to take this derivative, figure out where it's equal to 0. And luckily for us, I'm going to add 4x's to both sides. And we find out that x equals 20. So it seems to be the case that we're going to optimize things when this distance right here is 20. But we need to double check and make sure that that's actually a max, not a min. So we're going to do our first derivative sign chart. I got a prime on the top and a on the bottom. There's my 20. If I imagine taking and plugging in something just to the left of 20 into this orange equation right here, then I get a number that is positive. If I imagine plugging in something bigger than 20 to this orange equation, then I get something that is definitely negative. Let's fully label our sign chart with increase, decrease. And as a double check, we see that, yep, we go from increasing to decreasing. So we have max area when x equals 20. Now let's go back to the problem and see if we've actually answered the problem. So when I go back up north to the problem, this problem asks me what are the dimensions right here. So I'm close to finished. I've told them one of the dimensions. I've told them that x had better be 20. We need to find y as well. So I can just plug this 20 right here into this blue equation to find out that y is 80 minus 2 times 20, or 40. So apparently, if I build a rectangular pen that's 20 by 40, I will get the maximum area. Let's take a look at another classic problem. Next on our problem, you might come across things that ask you about cost of materials. So you can imagine being in business and wanting the materials of things to be at a minimum cost. It'll help you maximize profit. Here's an example of one of those types of questions. I've got a cylindrical can, and it can hold 20 meters cubed of volume. Then it starts telling me cost. It tells me the materials for the top and the bottom cost 10 bucks per meter squared, and the materials for the sides are a little cheaper, $8 per meter squared. We want to find the radius and the height for the most economical can. Now we need to be savvy about that. What they're actually saying when they say economical can is they're talking about a minimum for price. So as you can imagine, in a minute we're going to have to do a price function. Let's start at the beginning by sketching our cylinder, sketching our picture. So on my cylinder, I have a height, I have a radius, and we got to figure out the height and the radius that minimizes our price. Now let's list out our knowns. One thing I know is that the can hold 20 meters cubed, and that's volume, because you have cubed for your unit. So let's write the volume formula of a cylinder, which we know by heart or can easily look up. We got pi r squared times the height. And according to this problem, the volume can equal 20. So let's do 20 equals pi r squared h. We're going to come back and use this in just a second. Now this problem says that we're optimizing price. So let's make a price equation. Now if you imagine the the price equation, we're going to take $10, we're going to multiply it by the area of the top and bottom, plus we're going to have to take $8 times the area of the sides. So we're going to take $10 times the area of the top and the bottom, $8 times the area of the sides. Now let's go filling in what we can. The first thing I notice is that the top and bottom of a cylinder are both circles, and so in order to find the area of the top and the bottom, we just know that the top is a circle, its area is pi r squared. The bottom is also a circle, so its area is pi r squared. Now we've got to do $8 times the area of a side. Now the area of the side is a little trickier, but luckily for us we remember the formula for the surface area of a cylinder. I'm going to write it over here to the side. The surface area of a cylinder is 2 pi r squareds plus 2 pi r h. The 2 pi r squareds right here, that's the top and the bottom, which we already found over here. That means that the 2 pi r h's has to be the sides, the area of the sides. So let's take this part right here, the 2 pi r h's, we're going to substitute it in for the area of the sides. There we go. I'm going to distribute this out and simplify a little bit, and then we'll deal with this guy. So I've got price equals, I have a pi r squared plus another one. That gives me a total of 2 pi r squareds in here. When I take these 2 pi r squareds and multiply by 10, it gives me 20 pi r squareds plus, and then I have 16 pi r h's. Now what I notice is this pink equation has two variables, which is a problem. If you ever have two variables, then we're going to go back to our known information that's over here, and we're going to isolate one of those variables. Now, if I look at this known equation right here, then I see that I could isolate h, or I could isolate r, but honestly it looks like it's a lot easier to isolate h, so let's do that. I'm going to go over to the side right here. Let's just divide everybody by pi r squared. Those will cancel, and we get h equals 20 over pi r squareds. Whew. Now we can take this and substitute it in for h right there.